This video is entitled Taylor Polynomials. A Taylor polynomial, hence the name, is a polynomial approximation of a function near some value we call c, which means centered at c. Now it can be any degree that you want. The higher the degree, the better the approximation. What this graph is showing you here is I just kind of sketched out an f of x, and this would be the shape of a cubic polynomial with the leading term being x cubed being positive, would go this direction. But the idea is trying to show you that if this was the Taylor polynomial for this graph at c, notice how the polynomial is pretty darn close to the blue function graph right around that point. Then it goes off separate directions. So the idea is that the polynomial is used to approximate a value on the function close to that c. All right, so let's come down here and take a look at this. Now we're going to look at nth Taylor polynomial, nth degree, whatever, basically nth degree, and nth degree Maclaurin polynomial. Maclaurin polynomial is just a Taylor polynomial centered at c equals 0. Maclaurin was also another mathematician like Brooke Taylor. Maybe they worked on this together or something. I don't know. But anyway, it can go on theoretically, on and on how many terms you want. But obviously, we don't want to get that carried away with this. But here's how it would expand to whatever n degree polynomial you wanted. It would be f of c plus f prime of c times x minus c plus f double prime at c over 2 factorial. 2 factorial, of course, is 2 times 1. X minus c squared. Third derivative at c over 3 factorial, x minus c cubed. And it would just keep following that pattern on and on. Next one would be 4th degree at c over 4 factorial, x minus c to the 4th. So it would keep going on and on and on. And then once again, I'm mentioning Maclaurin polynomial. So we're going to find a Maclaurin polynomial when n equals 4, a 4th degree one. And we're going to use it to approximate what e to the point 2 would be. And if we're doing e to the 2x, that means x would be 0.1. So the idea is that we create this polynomial and we plug in 0.1. We're going to see how close that matches to the calculator output. Now, of course, the calculator has to use some sort of algorithm also. But this, it's hard to get an appreciation. This is more of a historical perspective, but I got a little something you'll see explaining it coming up a little later. But alrighty, so 4th degree, I need 4 derivatives. Okay, I like to use functions that aren't hard to differentiate. The chain rule just keeps putting a 2 out in front of all these. And then we're evaluating these at center 0. So 1, 2, 4, 8, 16. So we kind of have everything we need. We're ready to plug it into the formula. So we have f of 0, which is 1. F prime is 0, which is 2. That's going to be 2. That'll be x. The next one will be f double prime of 0, which is 4, divided by 2 factorial, 2 times 1. The third derivative of 0 is 8 over 3 factorial, 3, 2, 1, x cubed. And then fourth derivative at 0 is 16 over 4 factorial, x to the 4th. So that's basically Taylor polynomial, and it's written like this way. I just went ahead and reduced it, but it's not mathematically wrong if the fractions aren't reduced. So what we're saying is this 4th degree polynomial right here, I won't read out all the terms since you're just look at what I'm pointing at here. If I plug in 0.1 for x and then plug in 0.2, e to the 0.2 in the calculator, it should be very, very close. But the idea, that's why I picked 0.1, something close to 0. We're centered at 0, so we want to evaluate 0.1. The idea on this is it's not necessarily supposed to work if you get far away from the center. It's only supposed to work. In fact, check out the graphs here. The blue is the e to the 2x, and then the red is the fourth degree polynomial, well, it's hard to even, it's almost looks like it's right on top of it there, around the neighborhood of 0 there. So that's a good sign. But you see, of course, it quickly separates going in the negative direction for x, and then it starts separating as you go the positive direction of the x. But that's okay. It's only supposed to work in the immediate neighborhood of whatever the value of c is, which of course is 0. So what I did is I put in e to the 2x in the calculator for y1. I typed in the polynomial for y2. And then I kind of put a table of values in right here. And let me zoom in this a little bit. But over here, I use the function value to do y of 1.1, 1.2214, blah, 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 and then putting in 0.1 into the polynomial. You get 1.2214. So yes, believe it or not, back in the olden days, you could, you could actually manually calculate that polynomial with putting 0.1 in there and doing all the multiplication. I know it's probably surprising to people, but it would have taken a little bit of time, but it could have been done. But yeah, but anyway, long story short, this is a darn good approximation. In fact, to the first 4 decimals, that's all there is in the polynomial. It's just 4 decimals, but yeah, that's pretty close. So all I did here was I started at 0. I guess I could have also gone the negative direction, but it quickly separates in the negative direction. I just went the positive direction. So 0.5, it's still kind of close. When x is 1, you see it starts separating a little bit right there. And then you get to 1.5, and it starts separating more. And look at 2, it's really far apart at 2. But that's okay. The idea was it's supposed to work at in the neighborhood of 0, which 0.1 is very close to the neighborhood of 0. I could have put in like negative 0.1, and that would have been also a very good approximation. And I just used the Maple software. It's not required in any of my classes, but I just use the Maple software to evaluate the Taylor polynomial. And there it is. So it kind of matches what I got right up here. So that makes me feel like I probably did okay there. And my approximation was pretty close, so. All right. Now we're going to find the 4th degree Taylor polynomial for f of x equals natural log of x. And this time we're centering it at c equals 1. Couldn't really do 0 here because you'd have some serious issues here plugging in 0 in for ln. ln of 0 is undefined, and you would have a bunch of divide by zeros here, so that would be no good. All right, so let's just take the 4 derivatives. ln of x will be 1 over x, which is x to the negative 1. And so I just kind of took the derivatives using the negative exponent and then rewrote them without it. So it'd be negative x to the negative 2. Negative 2 times negative 1 is 2. Makes that x to the negative 3. And then negative 3 times 2 is negative 6. X to the negative 4. Plug in 1 in each one of those. You get 0. You'll get 1 right here. That'll be negative 1 over 1 squared. This will be 2 over 1 cubed, which is 2. And then negative 6 over 1 to the 4th, which will be negative 6. So now we are ready to plug this in to the Taylor polynomial. All right. This really isn't too difficult. It's just kind of a plug and chug thing here. So f of 1 here is going to be 0, so we'll lose that term. F prime of 1 is 1, and now we have x minus 1. And then f double prime at 1 is negative 1, so it's negative 1 over 2 factorial, which will be negative 1/2, x minus 1 squared. Third derivative at 1 is 2 over 3 factorial is 2 over 6, x minus 1 cubed. And then the fourth derivative is negative 6 over 4 factorial. 4 factorial is 4321. So it's negative 6 over 4 factorial. And that'll reduce to 1/4. x minus 1 to the fourth. And there would be no need to expand all these things out. You know, often students will ask me, do we have to expand all that out? Oh, no, that's completely unnecessary. That's perfectly good right there. So let's see if did I pick a value for this one to test or not? No, I didn't, but let me just show you. I picked some values here. Just, you know, there's 1. We're centered at 1. And you see I have everything typed in right over here. So y1 is whatever ln's using in the algorithm ln's using in the calculator. And y2 is our polynomial. Now, it's only showing a certain number of decimal places. If we had more decimal places, you would start seeing a difference. But anyway, so, you know, you go right below 1 a little bit, and look how close it is. 0.9, 0.8, 0.7 are all very, very close. 1.1, 1.2, 1.3. Start separating a little bit at 1.3. I didn't show any more extreme values, but it would have started separating from there. But it's a very good representation in the neighborhood of 1. Now, I put a little blurb here just to mention that, you know, why create a polynomial and do all this to do something, you know, that we can do in the calculator. Of course, as I mentioned there, the calculator is obviously using some sort of algorithm. Maybe not Taylor polynomials, but it's using something, because it just, you know, something like e to the 0.2 can't just be, it's not like working out 2 to the third power or something, you know, where you can go 2 times 2 is 8. 2 times 2 times 2 is 8. But you have to have some way to do it. But anyway, this would, yeah, but why would you, you know, create a polynomial when you don't have to? But the idea is because this leads to an idea called Taylor series, which Taylor series can then be used to represent certain functions. So we're going to see, you know, possibly see how functions are rewritten in terms of series, like sine of x, cos of x, e to the x, ln of x, and others can be represented as a Taylor series. So this idea has merit in that respect, is following this pattern and rewriting it as a series to represent that function. So, all right, let's take a look at another one here. Looks like this will be the last one, and that's basically it. It's nothing, no more new ideas in this section other than just trying some examples. This one we're doing a 5th degree polynomial, because actually what happens here, this, you know, it could be possible that if you just pick some random degree, you won't be able to do it because you might get a term that goes to 0. So notice what I'm kind of jumping ahead here for a second, but I just want to show you. Notice that the 4th derivative here is 0. So I could not have a 4th degree. I could do a 3rd degree, or I can do a 5th degree. I could not do a 4th degree because that's 0. So that's why I went ahead and chose 5th degree here. So we're centered at pi over 2, sine of 2x. Let's take these derivatives. We got chain rule, and of course we have alternating, and then we got pluses and minuses. So sine of 2x will have a derivative 2 cos of 2x. Another 2 makes 4, but the derivative of cos is negative sine. And the negative will stay there. When we bring out another 2 makes 8, so it becomes cosine. Now the derivative of that cosine makes a negative sign, which turns this negative back to positive, keeps bringing 2's out, so now we have a 16. Then the derivative of 16 of 2 sine of 2x then will be 32 cos of 2x. So all these sine terms, when you put pi over 2 in there, 2 times pi over 2 is pi, so they're all 0. So the first, third, this the original, the second, and the fourth, all are going to be 0. But cosine of pi is negative 1. So 2 times negative 1 is negative 2. Negative 8 times negative 1 is positive 8. 32 times negative 1 is negative 32. So we kind of have some missing terms here this time. So there's the polynomial formula. So I just kind of skipped over the ones we didn't need, like this one, and then this one right here, and then the fourth we won't need. But this one, f prime of pi over 2 was negative 2 times x minus pi over 2, plus we jump over to the third. f third derivative, f triple prime, whatever you want to call it, of pi over 2 is 8. It's 8 over 3 factorial, which is 8 over 6. X minus pi over 2 cubed. And then for the fifth term, the fifth derivative at pi over 2 is negative 32. And the 120 comes from 5 factorial, which will be on the bottom. So 5 factorial, 5 times 4 times 3 times 2 times 1. Of course, this reduces. And then I just did another visual illustration. Oh, went too far. There's the maple result. Oh, maple just distributed this thing right here. That's okay. Rest of it's the same. So obviously that probably means I'm right. But then we can look at the results. So I'll put them in here and look at the graph here. Boy, look at the red and the blue practically overlap right there between. So there's pi over 2. I scaled it. I labeled that to indicate the scaling is pi over 4. And so that would be pi over 2, and that would be 3 pi over 4. But yeah, that's right over it here, isn't it? Yeah. Now, this is in radian mode right here. That's always the best way to graph trig functions. So pi over 2 is 1.57 radians, so I didn't actually put that number in there. But I just picked values around 1.57, and you can see they are very, very close. So I think we did a good job with that Taylor polynomial for sine of 2x, centered at pi over 2. All right, well, I think that's going to take care of this video for Taylor polynomials.